Now let's talk about a slightly more advanced topic in linear algebra, which relates to notions of range and linear independence in matrices. To begin with, for a matrix A, which is m by n, the range of A, which we're going to write script r of A, this is the set of all vectors that can be written as ax for some x in Rn. So the range of A, which this symbol here means it is a subset of Rm, this is the set of all vectors that can be written as A times x for some x in Rn. So remember that this product here can also be written as the sum from I equals 1 to n of ai, the ith column of A, times xi. So this is really the set of all vectors that can be written as a linear combination of the rows of A. And we say that the columns of A are linearly independent if no column is in the range of the remaining columns. And the way we write that is that ai, this is the ith column of A, is not in the range of A minus I. So A minus I here would be the matrix where we take out the ith column. So there's no AI column anymore. The AN. So AI is not in the range of this. That means we can't come up with some linear combination of these other columns that equals A. Now the rank of A for a matrix in M, which is m by n, is just the number of linearly independent columns. This is a slight simplification of wording here, because really what it is it's the dimension of the largest set of linearly independent columns, but we'll just be a little bit informal here and just refer to it as the number of linearly independent columns, as long as you understand what that really means. And there are some important properties of the rank. First of all, the rank of A actually equals the rank of A transpose. This is not immediately obvious, but it's a very fundamental property of matrices that the rank of A is always equal to the rank of A transpose. So we could have defined everything in terms of rank and linear independence in terms of the rows of A instead of its columns. And that would give the same definition of rank because the rank of A transpose equals the rank of A. And finally, for a n by n matrix here, the rank of A being equal to n, this is equivalent to, first of all, Ra being the set of all vectors in Rn. So if the rank of A is n, then we can form any vector in Rn as a linear combination of the rows of A. And this is also equivalent to A being non-singular. It means we can find an inverse of A. Another important property for vectors matrices is that of orthogonality. So for vectors, for two vectors, x and y, both in Rn, we say these vectors are orthogonal if their inner product is 0. We take the inner product of x and y. If that is 0, then we say that x and y are orthogonal. And further, they're called orthonormal if the norm of x equals the norm of y, and that equals 1. The normal term here comes from x and y, in this case being normalized to have L2 norm equal to 1. An orthogonal matrix, so we could say a matrix U, a square matrix n by n, is orthogonal if all of its columns are orthonormal. So U here is a matrix, U1, U2, these are the columns of U, to UN. And we say that this matrix is orthogonal if all these elements here are orthonormal. That is, if we take any ui transpose uj, if that equals 0 for all I not equal to j, and if all of these columns have unit norm, unit L2 norm, then we say the matrix is orthogonal. It's important to note that an orthogonal matrix actually has orthonormal columns. So it's both has orthogonal columns and that are also normalized. But a nice property here, which follows very immediately from this definition, is that U transpose times U, that's the matrix of all these inner products here, right? But this inner product is 0 unless I equals J. And so this matrix product here is just equal to the identity. It has 1s in the diagonal and 0s everywhere else. This is also equal to U transpose. And so what this shows is that for an orthogonal matrix, the inverse of U is actually given by U transpose. So U inverse actually equals U transpose. And this is very nice because computing inverses in general can be somewhat time-consuming and costly, but computing a transpose can be relatively quite easy. So inverses for orthogonal matrices are very nice. And finally, it should be hopefully apparent that the columns of an orthogonal matrix, and also the rows too, because the transpose of an orthogonal matrix is also an orthogonal matrix, the columns of an orthogonal matrix are all going to be linearly independent. You can see this in many ways, maybe most obviously just by the fact that it has an inverse. Therefore, the columns have to be linearly independent, has to have full rank, and so the rank of U, for example, the rank of U has to equal 1. Sorry, has to equal n. Finally, the null space of A for matrix A in M by n, the null space of A is a set of all vectors x such that A times x equals 0. So the null space of A is some subset of Rn, because x here has to be n-dimensional in order for this matrix vector product to make sense, and it's the set of all vectors in Rn such that when you multiply them by A, the result you get is an all-zero vector. Now, a very nice property of the range and null space is that the range of A and the null space of A transpose are what are called orthogonal complements. That is, the range of A and the null space of A transpose, their union is equal to all of Rm. These are both subspaces of Rm because the null space of A transpose will be a subspace of Rm. These together, their union gives you all of Rm, and their intersection is just the 0 point. There's no other point in both of these. One way of thinking about this is if we take any vector x in the range of, A, and a vector y in the null space of A, these two vectors will be orthogonal. So y transpose times x will equal 0. And any vector z can be written as some combination x plus y, where x is a vector in Ra and y is a vector in the null space of A transpose. We're not going to prove this here, but this property of the range of A and the null space of A transpose is one of the more fundamental properties of the range and null space of matrices in general.